Good evening, everyone. It is our March Speakers Night for 2024. Welcome to Rask Toronto Centre. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of the Rask Toronto Centre. This is our Speakers Night presentation. Please note that this meeting is, in fact, online only and not at Ontario Science Centre. And just to start off this fun little March meeting, I just wanted to wish everybody happy equinox yesterday. Happy penumbral eclipse coming up this 24th to 25th. And of course, happy almost solar eclipse in April 8th. Very exciting time for astronomy. We have all kinds of things happening in this particular show. Our president, Tom Luton, will be talking about various programs later on this evening. But first, we do have a special event to kick off. So I'd like to go ahead and get us started here by acknowledging that the Royal Astronomical Society of Canada, RASC Toronto Centre, meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. So this is, of course, as I mentioned, our speakers night, and I have the great pleasure of introducing our fantastic speaker tonight. We have joining us this evening Marianna Veltri from the Physics and Astronomy program at York University. I also, of course, have a little bit of an extra happy time to introduce her because, as the director of the observatory, I actually got to supervise her for a little bit. She has been part of the observatory team at the LNI Carswell Observatory since 2022, helping to do all kinds of wonderful things in astronomical research, in particular with the 1 meter telescope, hosting large tour groups, and she's one of our very few officially certified atrium tour leaders, and was recently the lead designer on one of our major outreach efforts as image designer, completing a total array of over 40 science-based informational graphics, providing information throughout the entire observatory and leading the observatory treasure hunt. And if that's not even enough, of course, speaking of treasure, Mariana is also currently the treasurer for the Astronomy Club at York University. Of course, this luminous source of astronomy joining us tonight has an energetic research project as well, which she's going to get to tell you about tonight. She is, of course, right now also doing research at York University around the work of quasars. And I'll let Mariana tell us about these extremely energetic black holes. It's all very exciting. And as they say, if you're not impressed by the idea of black holes, well, clearly you don't understand the gravity of the situation. So, Mariana, I'm going to go ahead and hand this over to you. Take it away and go ahead and help us investigate these luminous mysteries.
Thank you very much, Dr. Hyde, for that wonderful introduction and for allowing me this opportunity to speak about my experiences so far as an amateur astronomer. I'm super excited to share with all of you some spectacular spectra and talk about some really cool objects in our night sky. So, tonight I'll be talking about these extremely interesting objects in our night sky called quasars, and I'll be discussing the research that I'm a part of in regards to quasars and their spectra. Now, the breakdown for this presentation has a short agenda, which will be as follows. So first, I'm going to explain the research position that I'm a part of at York. And then we're going to start talking about active galactic nuclei and how quasars tie into that. And with that description of quasars, we'll get into a deeper description and get into detail about their supermassive black holes, their accretion disks, their jets, and their variability. Then we'll talk about spectroscopy and how the data for SDSS uses that. And then, of course, we're going to go through the basics for spectra and look at specifically quasar spectra. And once we become familiar with quasar spectra, we'll then compare their spectra to spectra of other objects like galaxies and stars. And then I'll make some concluding remarks and talk about a really interesting quasar, J2318, at the end. So, as mentioned previously, I am a student at York University, and at York, there are many opportunities to be part of research within your field of study. So, the image on the slide is actually of the 1 meter telescope at the Allen I. Carswell Observatory at York, which I was able to use for various research projects on galaxies and exoplanets and stars. And the Research at York program, or the RAY program, is a opportunity for undergraduates like myself to participate in research projects with other professors and other students. Now, my coworker Zezu and I, we work under Professor Hall at York University, and our RAY position in particular allows us to do research on quasars and more specifically quasar spectra. Our research consists of using spectral data from the Sloan Digital Sky Survey, and more specifically SDSS 5, and we use it to locate remarkable quasars and analyze their spectra. But before we get into the spectra of these really cool objects, it's important to know a little bit about these celestial bodies beforehand. So it's important to note that quasars are a type of active galactic nuclei, or AGN for short. But what even are active galactic nuclei? Well, within the central regions of some galaxies, there exists an active nucleus which could outshine its parent galaxy or outshine its host galaxy. Now, this luminosity is due to the activity within the nucleus of the galaxy, which could consist of, let's say, gas and dust falling into a black hole. So that gives us the name active galactic nuclei. Now, there are many different types of AGNs, and since astronomers can't always agree on the names and classifications of objects, this can make the classifications of AGNs a little tricky sometimes. So, one main way of classifying AGNs is based on the luminosity itself. So, some examples of AGNs are shown on the slide here. So, this is the view from Earth. This would be us, and our line of sight would be in this general direction. So, Seyfert galaxies, they were named after Carl Seyfert, and they are a type of AGN where the nucleus has about the same luminosity as its parent galaxy and are usually located much closer to us. Now, you can see on this image these cone like shapes on these AGNs, and these represent jets, which we'll talk about shortly. Now, quasars are also a type of AGN, which are more powerful and they can have luminosities up to 1,000 times more than its host galaxy. So that means that quasars could outshine their parent galaxies altogether. Quasars also sometimes have these jets, again, which we'll discuss shortly. However, their jets are usually not aligned with respect to our line of sight. So if this is us here on Earth and we're looking at these quasars, their jets are usually pointed at different directions and not really pointed directly towards us. Now, the last type of AGN, which we can see on the image, they are blazars, which also have jets. However, their jets are aligned or mostly aligned with respect to our line of sight from Earth. So if we look at the blazars, we can see their jets point directly towards us or basically directly towards us. So it's kind of like having a flashlight pointed directly into your eyes. So now that we understand what active galactic nuclei are, let's begin our discussion on one specific type of AGN, quasars. So, quasars consist of supermassive black holes, or SMBH for short, at the center of massive galaxies, and they are surrounded by a rapidly rotating accretion disk. Quasars are extremely luminous due to matter converting gravitational potential energy into thermal and non thermal radiation through collisions as matter spirals into the supermassive black hole from the accretion disk. So this would mean that all quasars are AGNs, but not all AGNs are quasars. Now, both images on the slide, they represent AGNs and they could specifically represent quasars. So in the image on the left here, we have a supermassive black hole and then a bright, rapidly rotating accretion disk around it, and then this kind of jet of light. The image on the right, we have something similar. We have the black hole in the center, the accretion disk around it with some torus of gas and dust, and then these jets, which we'll talk about soon. Now, quasar redshifts are actually a very important key to to understanding quasar spectra and the structure of quasars and their behavior as well. And they are usually measured from the strong spectral lines that dominate their visible and ultraviolet spectra. Now, this is an important point that we'll come back to shortly. So the video here is a good visual on the general structure of quasars or what they could generally look like. So as you can see, when we zoom in, we have this rapidly rotating accretion disk that is rotating around the supermassive black hole. And then we have matter from the accretion disk actually falling into the supermassive black hole. And we can see again, once the video plays, that we also have this bright jet of light as well. Okay, so we know what quasars are in general, but now let's break down this understanding and get into the specifics. So let's first talk about the black hole and its accretion disk. So quasars consist of supermassive black holes, which could have masses spanning from hundreds to billions of times the sun's mass. And around this black hole is an accretion disk that is made up of matter such as gas and dust, which actually rotates around the black hole. The matter closer to the black hole rotates around the black hole more quickly than the matter that is further away from the black hole. And this is due, of course, to the conservation of angular momentum. And as the accretion disk rotates, material from this disk falls into the black hole. Now, the video on the slide is another good demonstration of the structure of quasars and what they could look like. So we have the rapidly rotating accretion disk. It's bright and is rotating around the supermassive black hole. And then we can actually see matter from the accretion disk falling into the black hole, and then these jet-like features as well. So, as mentioned previously, quasars are extremely luminous due to matter from this accretion disk converting gravitational potential energy into radiation through collisions as the matter spirals into the black hole. Now, some matter within the accretion disk is theorized to be from surrounding stars within the galaxy itself. However, quasars are still able to outshine their parent galaxies and outshine these stars. And now, while I won't get into great details about the structure of the accretion disk in specific, they do depend on a variety of parameters such as magnetic field, jets, and more. So, speaking of jets, many times when you look up images of quasars, you will see images like the ones here on the slide, which display these jet type features. Now, as mentioned previously, quasar jets are usually aligned at different angles with respect to our line of sight from here on Earth. And while many quasars do have these cool looking jets, not all of them do, or maybe it's better to say that they're not as strong or as prominent. So, jets appear to originate from the center of quasars and then they extend into outer lobes. And the appearance of jets actually suggests that the particles and energy are being transported from a compact source to outer extended regions. And these jets are also believed to be emitted at speeds close to light. So if we take a look on the image on the right over here, we have a quasar. And again, we have the supermassive black hole, the accretion disk around it, and then the jet as well. And again, the jet is faced at different angles. Now, blazars were mentioned previously, and they also have jets. However, their jets are faced directly towards us. So, this bright circle in the middle is actually its jet, and it's kind of blocking our view of the black hole, although we still can see some of its accretion disk. So, with this being said, there are supported theories as to why some quasars have powerful jets and how these jets actually form. So it was found that radio loud quasars, which are quasars that have strong sources of radio wavelength emissions, could have these powerful jets. Now, radio quiet quasars could still have jets, but they would be weak or maybe not as prominent. It is also suggested that in order for a quasar to produce these powerful jets, the quasar must have a rapidly spinning supermassive black hole, a bright black hole corona, which are the locations that are above and below the accretion disk that have regions of hot gas, and have to be powered further by strong magnetic fields. So the image over here, this is an image of a quasar, what we would see at multiple different wavelengths. But if we were just to look at the quasar with, let's say, visible light, so what you can see with your eyes, you would see something like this image down here on the left, where it would just look like a galaxy, or maybe it just looks like a star to you. Now, this pink gas, or this dust, maybe this sphere, is actually what you would see with when looking at X-ray light from the quasar. And the jets that are in blue are radio light. So if you were to use a radio telescope to look at the quasar, you would be able to see jets like these. Now, quasars are known to be variable in every waveband, such as visible wavelengths, and they are found to vary in magnitude, or in other words, they can appear to brighten or appear to dim slightly over timescales of months or even sometimes timescales of days. Now, this variability can be seen in quasar spectra through changes in their broad absorption lines, which I'll be explaining in detail shortly. The variability of quasars means that the data you collect of a specific quasar, for example, your spectral data, can seem to change over data sets that were taken at different time periods. And since this variability can occur across the entire electromagnetic spectrum, information on its dynamics, its structure, and the evolution of quasars could be studied in great detail. And this variability is extremely interesting, and if studied properly, it could help astronomers form a better understanding of the quasar behavior and better our understanding of the formation and evolution of the parent galaxy itself. So now that we have a good understanding of what quasars are and how they behave, let's talk about spectroscopy and how I, along with many other astronomers, study spectra of quasars. So, spectroscopy is the study of the emission and absorption of light and other radiation from objects such as quasars. Now, the image here is of the electromagnetic spectrum, and this blown up portion here shows us mostly the visible light, which would span from around 4,000 to 10,000 angstroms, which is what you would see with your own eyes. And then, of course, we have the ultraviolet wavelength to the left of it and the infrared to the right of it. Now, soon I'll be showing spectra from SDSS, and you will see that the spectra usually span wavelengths from around 4,000 to 10,000 angstroms, and we'll take a look at that very shortly. So, as I mentioned previously, my research consists of using spectral data from the Sloan Digital Sky Survey, or SDSS, and more specifically SDSS 5, and I use it to locate remarkable quasars and analyze their spectra. Now, there are two observatories which the data from SDSS originates from. The first one being the La Campañas Observatory, or LCO, in Chile, and an image of this observatory is here on the left. And the other observatory is the Apache Point Observatory, or APO, in the USA, with there's an image over here on the right. Now, SDSS 5 is an all-sky, multi-epoch spectroscopic survey, which provides optical and near-infrared fiber spectroscopy for millions of objects. So, numerous observations have been done on many different objects, which allows astronomers to compare spectra at objects taken at different times. Now, this is extremely useful for variable objects such as quasars, since it allows us to see how much an object has changed or how much the object has varied over time. Now, most of the data that I analyze, it comes from the SDSS 5's black hole mapper, or BHM. And the black hole mapper provides measurements for mass constraints, multi-wavelength spectral energy distribution, or SED, and the characterization of the variability of quasars. And since the data from SDSS-5 provides a large sample of quasar spectra, this allows myself and other astronomers the opportunity to identify remarkable or rare quasars and make some pretty cool discoveries. And I'll be mentioning one later on in the talk. So while I won't be showing the unpublished data from SDSS-5, I will be displaying some public spectral data from the Data Release 18 or DR18 to demonstrate what these spectra look like. So these are a few examples of the spectra from Data Release 18, and they were specifically taken from the SDSS Sky Server website, which is where all the public data is available. Now on the left here, we have an image of a galaxy, and directly above it, we have its corresponding spectra. And to the right of it, we have a picture of a quasar, and above that is its corresponding spectra. And just at a quick glance, you can tell that their spectra look very different because they're two different objects, of course. Now, at first glance, these spectra seem a bit intimidating to understand. However, I'll be going over the basics for understanding what you're looking at, and I'll show you how to distinguish quasar spectra from other objects like galaxies and stars. So, quasars do have a certain distinct feature in their spectra most of the time, and this is helpful in classifying them. And maybe you'll be able to figure out what that feature is before I actually point it out myself. So on this slide here, I have another spectrum of a quasar from data release 18, and I will be breaking down the different parts of the spectrum and show you how to understand the data. And I'll do this without going into any crazy amount of specifics or any crazy amount of details. So the image on the left is the quasar in question, and of course the spectrum on the right is the corresponding spectra. So on the spectrum, you can see some basic information given to us at the top over here in regards to the quasar itself, such as its right ascension and its declination and its redshift. And there is also information on the observation itself, like the program used, the plate number, or even the fiber number as well. And then, of course, directly below that, we have the actual spectrum, the actual data that was collected from that night. Now, let's break down the spectra so we can learn how to read the data. And we'll do this first by looking at the information provided to us at the top of the spectrum. So I've taken the information that's circled in red, and I just brought it down here so we can have a better look at it. So the right ascension and declination is given to us by RA and DEC. And this helps us locate the object in the night sky, its coordinates basically. The MJD is the modified Julian date, so basically the date and time that the data was taken. Now we're also given a redshift, which is this Z value over here with an associated uncertainty. Now when we look at quasar spectra in specific, we're always given a redshift. However, when we take a look at spectra for stars, they are not given a redshift, but instead they are actually given a velocity. So instead of seeing this Z value over here, you would see CZ, which would be the speed of light times a redshift. We'll look into star spectra soon. So we're also given the class, which is the classification of the object. So basically what the object actually is. For example, if it's a galaxy, a star, a quasar. And the classifications can actually get very specific and give the exact identification of an object. So for this spectrum here, the classification is given as QSO broadline, which stands for quasi-stellar object broadline. And this basically means that the object is classified as a quasar, or it could be a quasar, and more specifically, a broadline quasar. Now, like I said, we'll take a look at star spectra soon, and you will see that their classifications can get very specific. And this is great for astronomers since it helps them to really understand what spectra they're looking at, and it can help them find patterns in the behavior of these different types of stars. Now, some other information is given, such as the plate and the fiber number, and this is specific to the certain observation. So each object in the field of study is assigned a specific fiber on the telescope in order to collect data. So for this specific spectra and this quasar, the data was collected on fiber 50 out of a certain total number of fibers. I don't know what the total number is, but it's number 50 out of all of the fibers. So now that we understand the information that is provided to us at the top of the spectrum, let's figure out how to read the actual spectrum itself. So, as mentioned previously, spectroscopy is the study of the emission and absorption of light and other radiation from objects like quasars. So, spectra will show us this absorption and emission of light at different wavelengths for a particular object. So the graph itself is a plot of the wavelength in angstroms and the flux. And as mentioned previously, the wavelength ranges from around 4,000 to, this one says 9,000, but around 4,000 to 10,000 angstroms. Now, the recorded spectrum is in black. So the actual data that was taken is this black spectrum here. And then the gray spectrum behind it is actually the associated uncertainty, which is very important. Now, uncertainties are very important because they can give us clues to the accuracy of the recorded spectrum, which again is the black part of the spectrum. Now, there are instances where uncertainty bars could extend the entire spectrum, so from top to bottom. And this would mean that the uncertainty at that particular pixel is very large, so the data at that pixel should just be ignored. And an example of this can be seen in the spectrum on the left over here at around 5,200 angstroms. We can see this long bar of gray. So that is telling us that the information at that pixel has a very large uncertainty, so we should just ignore the data at that particular pixel. But the rest of the data, everything else in black, is good. Now, there are also instances where entire sections of these spectra could be all gray, which would mean that there are large uncertainties over large sections of wavelengths. And this can be seen in the spectrum on the right over here, between the wavelengths of 7,200 to 7,400 angstroms. And when this happens within the spectra, I personally tend not to look at the spectra or not use its data, since a lot of the data is unreliable, but it's really up to each astronomer. Now, it's important to understand these uncertainties while analyzing spectra because you don't want to be making conclusions from unreliable data, of course. Now, let's take a better look at the emission and absorption lines. So, the bumps or the spikes that you would see in the graph represent emission lines, and the troughs or the dips in the graph would represent absorption lines. And as you can see in both spectra here, the emission lines are pointed out with red arrows, and then the absorption lines are pointed out with blue arrows. Now, each emission line is marked with a corresponding component or a corresponding element, and that is telling you what is actually being emitted. And then for absorption, it's kind of understood in a similar way. So if we take a look on the spectrum on the right over here, this large emission over here is Lyman alpha emission because it's told to us at the top. And the other emission bumps as well are also labeled so we can see that this emission right here is of silicon 4 and so on. Now the spectrum on the left over here, it has emission and absorption. So if we look at this arrow right here, we can see that this is carbon 4 emission. And then we see this trough, which is understood to be carbon 4 absorption. So even though it's not directly labeled like emission is, it's understood that this would be the carbon 4 absorption. And this can similarly be seen for silicon 4. So we would understand this spike as being silicon 4 emission, and then the trough following that would be silicon 4 absorption. Now, these markings not only inform us on what is being emitted or what is being absorbed, but it can help determine if the given redshift is correct. So this Z value that we mentioned before is the redshift. And usually, if the elements are kind of perfectly aligned with the emission bumps, like directly in the center, that is a good indication that the redshift is correct most of the time. So if we take a look at both spectra, we'll look at the right one first. We can see that for each emission bump, the elements are aligned almost perfectly directly in the center of the emission bumps. So this would be a good indication that the given redshift, so the Z value up here, is basically perfect or pretty close to perfect. And then the same thing can be seen for the spectrum on the left. So if we look at silicon 4 and carbon 4, they're aligned perfectly with their emission bumps. So we can also assume that the redshift given to us is pretty much correct. Now here are some more spectra of different objects. And again, the emission lines are pointed out in red and the absorption lines are pointed out with blue arrows. So the spectrum on the left over here is actually of a star, and we can see that it has quite a bit of absorption. So I had previously mentioned that star spectra aren't really given a redshift, they are given a velocity. So the CZ value up here would be its velocity. And again, that would be the speed of light times its redshift. So if you really wanted the redshift of the star, it would basically be 0. Now, the spectrum on the right is of a galaxy, and you can see very thin lines of emission. Now, it is strong emission, but they're very thin. So, even with just a quick glance at both of these spectra, without the images at the bottom, we can make an educated guess that these are spectra of different objects. Besides the fact that the classification kind of gives away what it is. But besides that, both spectra look very different, so we can assume that these are very different objects. So now that we can understand and we can read these spectra, let's get into spectral analysis for quasars in specific. So I mentioned previously that quasars have a distinct feature that makes them stand out when classifying spectra. Now, these features are broad emission lines, or BELs, and broad absorption lines, or BALs. Now, the spectrum on the left over here, we looked at this one already, and we can see that it has these big bumps, which are emission. And we can see that this emission has a certain width to it. So I had put these red bars down here to show you the width of these emissions, and we can see that they're a couple hundred angstroms wide. So these broad emission lines are due to the width of the emission itself, the broadness of the emission. Now, the spectrum on the right has these troughs, these dips, which are absorption lines. And these troughs, which are indicated with these blue bars, show us that the width of these absorption lines are like 100 or maybe a couple hundred angstroms wide as well. So this is again showing us that these absorption lines have a width to them. They have a broadness to them. Now, the width of both these emission and absorption lines is what classifies them as being broad. Now, this would mean that if we were to specifically classify these spectra here, the spectrum on the left would be a broad emission line quasar, or a BEL quasar for short, like I have written down here. And then the spectrum on the right would be a broad absorption line quasar, or BAL quasar for short. Now, these broad bands of emission and absorptions are key features in quasars, and they rarely show up in spectra of other objects, which would make them identifying features for quasars. So, when you're looking at spectra, if you see these broad emission and broad absorption lines, that's a pretty good indication that that is a spectrum of a quasar. Now, there are some strong lines and very common lines for absorption and emission lines that are common for quasar spectra in particular. So, when we're looking at spectra, you would see a lot of these emission lines come up for quasars. So, some common emission lines would include Lyman alpha with a Lyman alpha force to the left of it. We would also have magnesium 2, silicon 4, and carbon 2 and 3, helium 2, and then H alpha, beta, and gamma. So, those would be common emission lines that you would see pop up regularly in quasar spectra. Now, the same thing could be said for absorption in quasar spectra. So, some common absorption lines you would see is oxygen 6, nitrogen 4, carbon 2, Lyman alpha again, silicon 4, and carbon 4 again, and then aluminum 3 and magnesium 2. So, again, we would see these pop up regularly when looking at quasar spectra. So, many of these common emission and absorption lines are seen in the spectra on the slide. For example, the spectrum on the left, we can see it has magnesium emission. This is magnesium 2. And we can again see that these emission lines are very broad. And then the spectrum on the right, which we looked at before, we have common emission lines like silicon 4 and carbon 4, which are followed by common absorption lines of also silicon 4 and carbon 4. Now, broad absorption lines in particular are thought to be due to quasar outflow when matter is lifted off the accretion disk. And the matter is then accelerated by radiation, which causes the absorption lines to appear blue shifted, meaning that the wavelength of light is being shortened, so the light seems to be shifted to the blue side of the spectrum or to the left side of the spectrum. And since these absorptions appear blue shifted, you will see the absorption troughs on the left side of the corresponding emission bumps usually. And we have a couple examples in front of us right now. So if we look at this carbon 4 emission, we can see directly to the left of it, the trough is carbon 4 absorption. So the absorption for this carbon 4 is directly to the left. It is blue shifted basically. And a similar thing can be seen for silicon 4. We have the silicon 4 emission and then followed by the silicon 4 absorption trough to the left of it. Now, we are aware that quasars are extremely variable in every waveband, and this variability could also be seen in quasar spectra through changes in the broad absorption lines. So, appearances, disappearances, and even strengthening of these broad absorption lines are signs that there are changes happening within the surrounding gas of the accretion disk. So, let's talk about the spectrum on the slide, for example. So, the spectra of this quasar was taken at a certain time and a certain date, so a certain MJD, which is given up here. However, let's say that we take more spectra of the same quasar 5 months later. The spectra 5 months later can show disappearances in the troughs or even strengthening in these troughs in this absorption. So the changes that we would see in and that we would observe in the spectra taken at the different dates are due to the quasar variability, hence the quasar changing over short periods of time. So on this slide here, I'm just showing some more spectra of quasars so we can become familiar with broad emission lines and broad absorption lines before we can go look at and compare spectra of other objects like galaxies and stars. So the spectrum on the left is a broad emission line quasar, and we can see because of the broad emissions of magnesium and the other emission as well. Now the spectrum on the right also has a broad emission line, and this is H alpha with nitrogen as well. However, for this spectrum, we can also see that there are narrow emission lines, and those are pointed out with green arrows. So, narrow emission lines are also common in quasar spectra, and sometimes even narrow absorption lines can be seen as well. Now, for quasars that just have narrow emission lines or narrow absorption lines, they would sometimes be called narrow emission line quasars or NEL, or narrow absorption line quasars or NAL. Now, again, there are some disagreements in regards to classifying quasars as broad emission line or broad absorption line or narrow emission line and narrow absorption line, since not all astronomers could agree on what is considered narrow and what is considered broad. So, for example, some astronomers would say that because of the broad emission of H alpha, this would be a broad emission line quasar. However, other astronomers would argue that this emission of H alpha is actually not broad at all, and there's much more narrow emission lines. So this would actually be a narrow emission line quasar. And although they can't agree on the specifics, they can both agree that this is still a spectrum of a quasar. So now that we are confident in our skills with understanding spectra, and we looked at many different spectra of quasars, let's compare this quasar spectra to spectra of other objects like galaxies and stars. And many examples of spectra from these different types of objects can be seen on the slide here. So you will soon see that while many of these spectra share similar features in their emission and their absorption, objects can still be distinguished fairly easy most of the time. And it's also important that while we compare spectra of different objects, that we keep in mind the broad emission lines and broad absorption lines that are common in quasar spectra and not really common in other spectra. So let's begin first with comparing stars and quasars. So the spectrum on the left is of a star, and we can see the absorption lines indicated with the blue arrows. However, these absorption lines are not broad. They're very, very narrow. We're also given the classification, so it's telling us this is a star, an A0 star, and we're also given the velocity as well instead of a redshift. So that's a pretty good indication that this is a spectrum of a star. Now, the quasar spectrum, on the other hand, on the right, which we looked at a lot, we know that these are emission lines and they're very broad. They have a width to them. We're also given the classification, of course, which is QSO broadline. And like I mentioned before, that means basically it's a quasar. And we're given a redshift. So we can be fairly certain that this is a spectrum of a quasar. Now, these two spectra here are still for a star and quasar, and you can see that both of these objects have strong absorption lines. However, they look quite different. So the absorption for the star, which is on the left, takes on kind of like a pointier dip, and there's much more absorption at different wavelengths. However, the quasar absorption, on the other hand, looks more like a trough, which with a rounded bottom. And we can also take note that the absorption for this quasar has silicon 4 and carbon 4 absorption, which again are common absorption lines for quasars, which we looked at a list earlier before. So while both these objects can show strong absorption in their spectra, it can get easier to decipher what is a star's absorption and what is a broad absorption line quasar when you start to recognize the patterns and the differences between their shapes, basically. So next, let's compare galaxy spectra with quasar spectra. Now, this can sometimes be difficult because quasars are a type of active galactic nuclei, as we talked about before, and they are located at the center of massive galaxies. So we can see how it can be difficult sometimes. So on the right side again, we have the quasar spectra with these broad emission lines, which we looked at many times already. And then the spectrum on the left is of a galaxy. And while it is evident that there is emission lines, there are no broad emission lines. And that is a key difference between the two spectra, is the broadness of these emission lines that are shown. And of course, we're also given the classification, so the class tells us what object we're looking at is. But even if they weren't there, we can still tell these two spectra apart. So these spectra here display absorption lines and emission lines. And again, we talked about the broad absorption lines that appear on the quasar spectra, which are unique to quasars themselves. And again, they're indicated with these blue arrows. However, we can also see absorption lines in this galaxy spectra. And while these absorption features do seem to have some width to them, they are not broad absorption lines. So the structure, the shape of the absorption lines are quite different when you compare the two. Now, certain features like this can also be due to iron, which can make it look like there's absorption happening within the spectra itself. And again, we're given the classifications of the object. So even if we couldn't distinguish what we're looking at, we can look for the classification for some help. So now that we understand quasars to a good depth and we can spot their spectra out of a bunch of other objects, what do we do with this information? Well, like I said before, we could use quasar spectra to understand the behavior, the structure, and the variability of quasars. And we can use a spectra to help us better understand the behavior and the evolution of its host galaxy. And while all of this is super cool, what's even cooler is when you find a rare or remarkable quasar. So, when looking at a lot of spectral data of quasars, you sometimes can find spectra that look unusual. And with this, you can figure out what unusual behavior this quasar is actually up to. So, this brings me to my final topic of J2318. So this is another quasar. So this is the picture of the quasar itself, and of course the corresponding spectra to the left of it. And while doing research, my team and I identified a remarkable quasar on SDSS 5, and we identified this quasar, which is referred to as J2318, as being an extremely high velocity outflow quasar with carbon 4 absorptions at a speed of around 81,000 kilometers per second, which is just under 0.3 times the speed of light, which is super cool. And while there's much more research being done on this quasar, and there's much more interesting things to say about this quasar, I just thought I'd use it as an example of the type of remarkable or rare quasars that I kept mentioning before. And as I'm nearing the end of this talk, I realized that there was a lot of information to take away, but I hope that some main things you take away is that spectral analysis stands as a primary avenue for investigating quasars, and given the presence of broad emission lines and broad absorption lines in quasar spectra, the interpretation of these spectra holds significant importance. And analyzing spectra of quasars can offer valuable insights about the behavior of quasars themselves and the behavior of their parent galaxies. So I just want to thank everybody for their time, and I want to thank Dr. Hyde and the whole team again for allowing me this opportunity to talk about my research with my team and to share with everybody some really interesting information on quasars and their spectra. So, of course, if there's any questions, I'll be happy to answer to the best of my ability.
Thank you very much, Mariana. As they say, black holes are timeless, but it sounds like you do have to be a bit lucky to spot a quasar or a really interesting quasar in that cases. So I'm going to, as I say, avoid any more black hole puns, but we do have a couple questions coming your way. So I'm actually going to pass you over to the official question section now. I think we have time for probably about maybe 10 minutes or so of questions from YouTube, and we've got a few that have come in during your talk. So, one of the first questions that came in, I'll go ahead and start with the earliest one first. Rask Toronto's question: what is the farthest distance look back that you, in light years, that a quasar has been found?
That's a great question. So, quasars are very far away from us. They're very old objects, and or celestial bodies, I would say. And I don't know what the furthest one would be. I'm not sure, but I know a lot. Like they're all very, very far from us, and they're very old, I guess you could say. But I don't know the farthest one ever found. That's a really good question, though. That would be really cool to look up after.
Oh, yeah, and it is a bit of an ongoing competition, so I'm not surprised you don't
Yeah.
have a constant number in your head because, of course, JWST has been coming out with all kinds of
Mhm.
new farthest distant ones. I know that they did have one that was at least 12.6 billion years old.
Mhm.
And,
Very, very old.
currently we're still in arguments about the age of the universe being 13.8 or
Yeah.
not.
Yeah.
So that's a hard one. And again, I would just encourage everyone to watch maybe science news or astronomy news article upcoming events because the new oldest or furthest is constantly changing.
Mhm.
So we have next up a couple comments. So there's a few comments that arrived, and this is all on the same theme. So what I'm going to do is I'm just going to give you the comments, and then we can talk about it. So we
Of
have a few
course.
comments from Guy Yenes from Santiago, Chile. He's asking about from a amateur's perspective. It seems like imaging a quasar with something like a UV filter combined with an IR filter, or something you could do to, I suppose, filter or select. And I think, given the comments, it's more like asking about photometric selections,
Mhm.
which I know you can do on quasars. So, do you have any, I suppose, I guess comments about that? If you're on an amateur telescope, obviously you can get your Johnson Cousins filters. So UBVGIR probably is a good set for that.
Mhm.
Um, do you have any photometric selections that you might recommend for amateurs?
So I feel like the easiest way to look at a quasar would be through just the visible light. So, like we talked about before, I don't know if my slides are showing, but through the visible light, those wavelengths. But you can of course look at quasars at different wavelengths, like the ultraviolet, infrared, X-ray, and that you would see different things. And quasars do vary. They are variable objects, like we mentioned, so they will change in all these wave bands. So if you were to look at, let's say, the quasar, even in visible light or any other light, it could change over time. So I feel like for amateur astronomers, if you just want to like take your telescope out to the backyard, I think the easiest would just to be look at the visible light spectrum. But if you do have telescopes that can look at ultraviolet, infrared, and get good data, that would be pretty cool. I think you should definitely do that.
Yeah, absolutely. And of course, radio telescopes are very easy to build if you have a wire and a stick, but hard to reduce the data for.
Yeah.
So I would watch out for that. And also, a lot of these targets do get quite, although they're very luminous, they do tend to get quite dim. I've seen a
Mhm.
lot of, I don't know about your catalog, but I know that a lot of the ones that I've seen up recently have all been 20-second magnitude objects.
Yeah, quasars can get very dim, and they can also get very bright. They'll vary, but, if you look at it with, a radio telescope like you mentioned, you can see or if there are jets, you can probably, um, identify the jets as well if you had a radio telescope, which that would be really cool.
Yeah, if you're willing to do the Fourier analysis, I think you're you're good with a wire and a stick, but it is a challenge mathematically for sure. All right,
Definite.
let's go on to the next question. This is moving on to our next one. Rask Toronto question: would the jets emitted from a black hole give us an insight to the potential internal structure of a black hole?
So that's a good question. So the studying the jets will help us understand or learn more about the quasar in general, and that would include the black hole and the accretion disk around it. It can kind of help us understand what is happening within this active nucleus within the galaxy. And I'm sure it could tell us some things about the black hole, of course, but I don't think it would be able to, or maybe with our technology, we won't be able to understand fully the direct center of the black hole, because that's definitely something I know a lot of people are researching. Black holes are a big thing because they're super cool, of course, but actually studying quasars because they have such a supermassive black hole and it's such an important part to their behavior. um, it would be a good place to start, I think, to definitely if you wanna learn more about black holes, to study the changes in quasars because they'll kind of all tie together. I believe the black hole, the accretion disk, the jets, all of that together, so I think it could possibly.
Yeah, absolutely, especially if you don't wanna get inside the event horizon. So,
Yeah.
as long as you don't wanna go inside the event horizon of a black hole, all things are possible, especially
Of
rotation and
course.
stuff like that.
Yes.
So next on a similar note, we do have another question that's a little bit about, sort of the quasar behavior. Next up, we have a question, from Lunacod2, who asks, "Can a suspicious quasar spectra," so suspicious being a fun word to use, maybe mysterious. Can a suspicious quasar spectra hint the potential presence of a Kardashev 3 type civilization? And of course, there's obviously a Kardashev fan, so I believe type 3 is where, in theory, again, sci fi related, you can harness all the energy in a galaxy. So a little bit of a fun one.
That's a great question. I think because the spectra that we look at, it's from the accretion disk. It's not the spectra of the black hole itself. So that we have to keep that in mind that the spectra is of the accretion disk that's around the black hole and gas and whatever that's around it. So that's a good question. I think studying it, you can, if you get a suspicious spectra, that would be a cool thing to look for or to try to research, I guess, because that's one thing when you're studying quasar spectra, you can find very common ones a lot. And then when you find a spectra that has odd behavior, you start thinking things like, okay, what could it be? Why is it acting like this? How is it behaving? And that can lead to many other possibilities and suggestions and ideas of what is going on with that quasar, what's going on with that object. So, yeah.
Excellent. Yeah, and of course, if you did find any life on other galaxies, you'd be having a heck of a time trying to communicate with them.
Yeah, I mean, that would be pretty cool.
That said, I don't believe there's substantial agreement as to whether or not Earth has even reached type 1 on the Kardashev scale. So we'll have to skip that one for now.
Yeah.
All right. So thank you very much for the answers, and of course we have a little follow up. So I believe someone was counting your slides. It looks like from Enyo, we have a question in slide 27: stars versus quasars. Is the left side of stars pretty generic, or is that a specific class of stars? I don't know if you remember that slide, but they're asking about is that star a specific star?
Okay, so I have 2 of those slides, and I'm assuming it's one of one of these ones. But, for that is a pretty well, because for stars, they have a lot of different spectra. Different stars, their spectra will look different. So that's why the classification is so important, because when you look at different stars like M stars, white dwarfs, so on and so forth, their spectra can look very different because a lot of times they're behaving very differently. So for these types of stars, I've seen these, spectra quite a bit, so they're not, I wouldn't say they're rare because I've seen them quite often. However, I don't study, star spectra specifically, so I don't know exactly what would be considered rare for a certain type of star because there's all the spectra for each star is so different. But from what I looked at through SDSS and all of the data that I've been seeing, this is very common. And I specifically looked for spectra like this because I knew I had absorption, spectra of stars, sorry, because I had this absorption and I knew I could compare it to quasar absorption. So I feel like these two that I'm showing are not uncommon at all, but we would have to get a star spectra expert in here to verify that.
Well, I could actually say that they are very typical. So that was a white
Mhm.
dwarf and an A star spectrum.
Yes, white
And
dwarfs look like that.
as you mentioned, it's completely accurate to say that every spectra of a star is an individual because of the stars, but
Mm,
for spectral types, you can make some generalizations. So those are actually
yes.
excellent prototypes that you picked for the white dwarf and the A star.
Yeah, the white
Um,
dwarfs we see a lot. Oops. So
yes, wonderful.
very interesting.
They're actually really fun, but yeah, that's probably a different talk.
You can go on a
um,
whole other talk about that. About
we could,
stars.
but we shouldn't. Not yet, not today. Um, all right, so let's go ahead. I think we have time for just a couple more quick questions, and then we'll be able to go to the next section. So we have one from Warren Gallagher. It looks like is there a reason the uncertainty bars are larger at 4,000 and 9,000, and does it make the use of 4,000 difficult? Um, so again, this sounds like it's referring to a specific slide.
Mhm. So for uncertainty bars, when they, like I was saying, when this gray bar spans the entire spectrum, that means information at the pixel, that there's a large uncertainty. So this could happen for a variety of different reasons. It can even just be the observation itself, if something happened while it was observing, while this observation was going on. So I feel like it could be a technical error, and it can really happen throughout the entire spectrum. Like there's no certain wavelength that would only have uncertainty. It's the entire spectrum can have all of these um, large uncertainties. And I think it's just because of like telescopes, like if things go wrong when you observe, of course, nothing ever goes perfect. So you're always going to have these uncertainties. So I think these are just specific examples where for the one on the left, this uncertainty was around 5,200 angstroms, and the one on the right is spanned from around 7,200 to 7,400 angstroms. But you can really find uncertainties like this throughout the entire spectrum, no specific wavelength.
Excellent, thanks. And I guess it looks like there's some extra interest as well for amateur astrophotographers. Another question from Lunicod 2: is there any way for amateur astrophotographers to participate in such projects? The idea of assisting such groundbreaking research is truly inspiring, and I'd be happy to volunteer. So, do you have any suggestions?
Yeah, so if you want to do, if you're interested in just doing the research on your own, all the data I showed, besides the remarkable quasar at the end, that's all public data from SDSS, and you can just go to their website and they have a bunch of spectra and a bunch of other data as well, which you can look at. But if you want to be part of certain projects, I'm sure there's many opportunities to volunteer at certain universities. Or if you actually go to the university itself, I'm sure you can find like Ray like research positions or work study positions as well. So the reason why I was able to do this is because I'm part of a research program that was at York. So that's why I had access and was able to learn about all this cool stuff. But I'm sure there's lots of volunteering opportunities as well where you can be part of things like this. But if you just want to do stuff on your own, there's public data which you can go all out and just look at and analyze yourself as well.
Wonderful. That's a great suggestion. And of course, for anyone else who's wondering, there are also easier barrier projects that you can get into under the banner of citizen science. So, in particular, I always recommend to people if you're looking for an easy way to get started helping citizen science projects like Galaxy Zoo and many, many, many others will let you contribute directly with kind of no barrier. You just go onto the website and click, yes, I want to join. All right, so we have one more quick one at the very end here. Final comment, follow up to another earlier comment. And I think this was follow up to Guy's earlier comment from Yanis, if I'm reading that correctly. So last one, visually identifying would be more difficult. That was, if I'm reading this right, the amateur astrophotographer's perspective. So again, using visual amateur astrophotography in the, sort of, I would guess, Johnson Cousins waveband to identify or pre-select quasars with some sort of photometric conditions.
Mhm.
Um, and I'll just say that there are a bunch of papers about photometric selections that can be made in the visual for quasars, and it's an active area of debate. So um, just watch out before diving into that completely.
Mhm.
All right. So I don't know if do you have any last comments, any last tips for amateur astrophotographers?
Any tips? I say if you can, even if you just go look at some spectra, even if it's not of quasars, but if you go to SDSS, their website, you can see all the spectra on so many different objects. And if you're really interested in stars, you can see how the different spectra look for different stars, which is very cool. So just go take a look and you can see firsthand, like it's easier to understand what I'm saying when you see it firsthand. You're like, oh, that's this. Oh, this is that star. So if you have time, if you're not busy, you should go look at some spectra because it's very cool.
Absolutely. I totally agree, and I as a little statement, I am a huge Spectra fan, so, I absolutely agree, and thank you so much, Mariana. I think that's the last question we have, time for tonight, so we're going to go ahead and wrap up, and I'm going to go back to the last transfer for this evening. So thanks again to our wonderful speaker, Marianna Veltri. You heard it all here, folks. Quasars are awesome. And I'm sure we could all stay here for quite a while, or at least I could, talking about spectra and quasars. But we do have to wrap up for now. So thank you once again, Marianna Veltri. And with that, we are going to hand over for our last transfer of this evening over to the president of the Toronto Centre RASC, Tom Luton, to go ahead and finish off the evening. Over to you, Tom.
Okay, well, thank you very much, Elena, and thank you very much to our wonderful speaker. And good evening, ladies and gentlemen, and thank you very much for joining us on this Wednesday evening. So, we've got some announcements, and let's get started. So, first of all, unfortunately, I have some extremely sad news if you have not heard this already. On March 5th, we lost a very good friend and a longtime, very important member of the Toronto Centre. Guy Nason passed in British Columbia. Guy was a longtime member of the Toronto Centre. He joined after the 1986 Comet Halley passage, and he was one of many people for whom the passage of that comet resulted in a lasting interest in astronomy. He was very important to the center. He held a number of positions on council and was Rask Toronto Centre president from 2000 to 2003. He was also a very important part of the CAO becoming part of the Toronto Centre, being one of the co-chairs, one of the first co-chairs of what is now the CAO committee. Guy Nason was a prolific asteroid occultation observer, to the point that unofficially the term being nascent has entered the lexicon to describe when, just at the absolute worst possible moment, a cloud pops up in the sky right at the spot you're trying to observe. Uh, Guy was, of all of, was a member of the society for many, many years. He was the first friend I made in the Toronto Centre when I joined the Toronto Centre in 2004. He will be sorely missed. So, moving on, I'd like to welcome you, those of you who have joined us. This is one of two types of meetings that we have here, the Royal Astronomical Society Toronto Centre. You've just seen one of our speaker nights, and in 2 weeks' time will be one of our recreational astronomy nights. For those of you who are joining us live, please use the YouTube chat and say hello. Enter some questions for presenters, as others have done already. If you're a new member of the Toronto Centre, please introduce yourself. And if you're coming to us from far outside the Toronto area, please let us know where you're coming from. So our next recreational astronomy night is Wednesday, the 3rd of April, 7:30 p.m., both online and in person at the Ontario Science Centre. Uh, Andy Beaton will be talking about the sky this month. Ralph Chu will be introducing the EC-CAR Astronomical Observatory to those of you who are new to the center and may not be familiar with our facility. And Joel Dick will be talking about Jewish astronomy and the Hebrew calendar. Please join us in person or live on YouTube. And then our next speakers night is Wednesday, the 17th of April, 7:30 p.m. online on YouTube. Professor Paul Schultz from York University will be talking about fast radio bursts. What are they and where do they come from? Now, we have solar observing at the Ontario Science Centre on Saturday, April 6th from 10 a.m. to 12 p.m. RASC volunteers will be setting up properly filtered telescopes in front of the building, and you'll get a chance to take a look at some solar phenomenon like sunspots and prominences. This is a weather dependent event, so please check our website for a go or no go call prior to attending. And speaking of solar events, so Monday, April 8th is a total solar eclipse. And I've received some questions and some emails about this, so I'd like to make this crystal clear at this point. There will be no Ontario Science Centre or RASC Toronto Centre events happening in the city related to the total solar eclipse. Now, several people have asked about this. Why are we not doing anything if there's an eclipse on our doorstep? And the answer is, to put it simply, there's an eclipse on our doorstep, but not overhead. Um, the vast majority of RASC Toronto Centre members will, quite frankly, be out of town watching this eclipse happen. Um, I, if I'd asked anyone to stay behind, they'd have laughed at me. If I'd ordered them to stay behind, they'd have laughed at me harder. Um, and as a result of this, the Ontario Science Centre has nobody to man their telescopes because we provide the majority of the equipment and the people who operate telescopes for all their astronomical events. And there's a follow up reason. If you recall back in August of 2017, there was a total solar eclipse that crossed North America, across the United States. From Toronto, it was around 70% covered. There were a fair number of Toronto Centre members who could not get the week off to go south and see this, but there were people like myself who could get the day off and could help with outreach. The Science Center expected approximately 500 people. They got in the neighborhood of 12,000. Now, the crowds got big enough that supposedly the police were on the verge of shutting the whole thing down. Um, the the Ontario Science Centre is a little worried about the possibilities of really large crowds. It's why they moved last fall's observing for the annular eclipse with partial from Toronto. They moved that to within the Ontario Science Centre grounds itself, rather than having it outside. So again, no RASC Toronto or Ontario Science Centre events will be happening relating to the eclipse on Monday, April the 8th. However, we still have a fair number of eclipse glasses that are available to be distributed. And if you happen to join us in person at the RAN in 2 weeks' time, you can pick up a pair or two. So please join us. Now, moving on to some observing sessions that are going to happen. The Bayview Village City Star Party for members only will be starting up again for the spring. The first clear night of either April 9th or 11th. So not the Wednesday. We're skipping Monday because obviously that's the eclipse. So 8 p.m. to 11 p.m. Please check out our website for a go no go decision based on the weather. Millennium Square public stargazing is starting up on Friday, April the 12th. From 6 p.m. to 11 p.m. Join us for an evening of free public stargazing along the North Shore of Lake Ontario at Millennium Square. Observe the moon, stars through our telescopes, check out the astronomy literature at our info booth, and ask us questions to learn more about the stars and planets. If you bring your own telescope, we'll gladly give you a hand setting it up and aiming it at the moon. Remember that it's cooler down by the lake, so dress appropriately. We still recommend wearing masks and using hand sanitizer. Please check our website for a go no go decision based on the weather before heading to the square. Coming up, the DDO Astronomy Speakers Night on Saturday, March the 23rd, 8 to 10 p.m. The eclipse or the RASC DDO team will be talking about what causes a lunar eclipse. Registration fee is as shown here. You can register online. The links can be found at rascto.ca. The CAO is open. Operations are largely back to pre-pandemic conditions, but there are a few exceptions. The major one being that we are at a maximum of 2 unrelated persons per bedroom who mutually agree to share said bedroom. Masking in common areas is encouraged, but is the preference of the folks in attendance will be taken. Please take a look at the CAO bookings page for all the details before you make your bookings. The job board. We are still looking for a few bodies. The Astronomy Center runs on volunteer energy. And to that end, we're looking for a volunteer committee chair, a marketing committee chair, and committee members. The EPO is always looking for additional help. Online presenters and telescope camera operators, virtual star parties. Reminder that in order to volunteer, you first must be a member. Drop me a line to president@rasto.ca if you'd like to help. Quick plug for the benefits of Rask membership. If you've liked what you see, and you'd like to join us, you can sign up or renew your membership online at secure.rask.ca. Gift memberships are also available. Contact the national office at mempub@rask.ca. And with that, I'd like to wish you all a very pleasant evening. Thank you very much for joining us. Please follow us on all the forms of social media that we have listed here. If you liked what you saw on YouTube, please like and subscribe and hit the notification bell. Stay safe and keep looking up. Good night, everyone.